Okay, welcome to class 4 of Physics 350. This class is on vector derivatives in other coordinate systems besides Cartesian coordinates, which we all know and love. And in terms of the textbook, this is actually section 1.4 of the textbook. We'll be coming back to section 1.3 in the next class on Green's theorem. So Cartesian and spherical coordinates, in Cartesian and spherical coordinates, it's fairly straightforward, in Cartesian coordinates rather, it's fairly straightforward to find the grad, div, and curl, and we did that a couple classes ago. And I'm going to introduce you to a new way of finding the grad, div, and curl and the volume element in spherical coordinates. And then in class, we'll be doing problems to extend that to to cylindrical coordinates. So we start off with an expression which says that the length, a small unit of length, is equal to a small unit in the x direction times x hat, plus a small unit in the y direction times y hat, plus a small unit in the z direction times z hat. And this is generally true, but for Cartesian coordinates, what's makes this expression especially simple is that the the unit, length in the x direction is just dx. Okay, so it's just dx. Since the x-axis doesn't shift from position to position, the dlx just becomes dx. Change in length in the y direction is dy, and change in length in the z direction is dz. For spherical coordinates, okay, so this is just a picture here of spherical coordinates with angle theta from the vertical radius r out here, and then angle phi coming around here. It's not shown here, but here's d phi. And so what would be the corresponding expression for a change in length, a infinitesimal change in length in spherical coordinates? Well, it would be, since these three vectors, the vectors r hat, which would point out in this direction, outward, and theta hat, which would point downward in the direction of increasing theta, and phi hat, which would point in the direction of this vector, are perpendicular, we can say that dl would be equal to the length in the r direction times r hat times the length in the theta direction, down this way, times theta hat, just down this way, plus a length in the phi direction times phi hat. Now, what are these lengths? Well, we have to look at the geometry. I can show you the answer here. In going outward from the origin, if we're at a distance r and we move directly outward, we just go out dr, okay, because r is already a length. However, if we move downward in the theta hat direction, if we move downward, then our length is not d theta, because theta is in radians, and d theta would not be a length in radians. And so if you think about it, this is a part of a circle, or an infinitesimal part of a circle, and so this length that would be inscribed when the vector here moves down by a amount d theta would just be r times d theta, right? Because it would be the radius times the arc length, or rather the radius times the angle would give the arc length r d theta. And then in the phi hat direction, it's even a little bit trickier, because the phi hat direction, it's a circle, but the greater as theta changes, the amount of length covered by a change in phi is going to decrease, right? Because if theta is 0, then changing phi doesn't change the length at all. So it turns out that it's equal to r times the sine of theta, which is this length here in the plane, times the infinitesimal d phi times phi hat. Okay, so just to summarize, our change in length for spherical coordinates would be dr r hat plus r d theta theta hat plus r sine theta d phi phi hat. Notice all three have units of length because the angles don't have units and sine doesn't have units. Okay, so how does that help us? Well, this length element turns out to be the key to understanding how to write the volume element, the gradient, the divergence, and the curl in spherical coordinates, and in, as we'll see in class, in cylindrical coordinates, and also in any, actually in any what's so-called orthogonal coordinate system, where the coordinates are always, the three unit vectors are always perpendicular to each other at each point. The ones we basically use are spherical and cylindrical, but other more complicated ones are possible. Anyway, so let's take a look at this expression. It's just a little bit imposing, but it just basically says that there's three directions, u, v, and w. For example, for Cartesian, this would be x, y, and z. And then we have a du, a dv, and a dw. So a movement in each of those directions. And then we have some function of the three variables, which turns du and dv and dw into a length, okay? And these functions are going to, these f, g, and h functions are going to be the keys to unlocking the expressions for the divergence and the curl and the volume element. So for Cartesian, as I said, the first coordinate is just the x hat, the second coordinate is just y hat, the third coordinate is z hat, and du is dx, dv is dy, dw is dz. And so we already have, we can say that because we just argued on the previous slide that dl was dx x hat plus dy y hat plus dz z hat, that these expressions f, g, and h should all just be equal to 1. Okay, so this should all just be equal to 1. So that we have 1 times dx x hat and 1 times dy y hat and 1 times dz z hat. Okay, spherical coordinates, a little bit more interesting. The first coordinate, again, is r hat. The second coordinate is theta hat, the polar angle. And the third coordinate is phi hat, the azimuthal angle. So it turns out, well, it doesn't turn out, we actually just showed, on the last slide, we argued that the infinitesimal length vector would be equal to dr r hat plus r d theta theta hat plus r sine theta d phi phi hat. So if we compare this, we have dr r hat up here, that's du u hat, times 1. So that would mean our f function would be 1. We have d theta theta hat, that would be dv v hat. That would mean that our g function here would be r. And then we have d phi phi hat, that would be dw w hat, correspond to dw w hat, and we would have r sine theta would be h. Okay, so our three functions which determine the infinitesimal length vector here are 1, r, and r sine theta, because that's what we multiply dr r hat, d theta theta hat, and d phi phi hat by to get the length vector. Okay, so these f, g, and h functions. Okay, so yeah, this is just the picture which we showed again, confirming that this was geometrically correct. But what about the gradient? Okay, so in Appendix A, it's worked out in some detail. I'm not going to go through the theory of this, but I just want you to know how to do this and have an idea that there is a systematic way of getting formulas for the gradient and the volume element and the divergence and the curl in different coordinate systems. In fact, in, as I said, any orthogonal coordinate system. The gradient turns out to be 1 over the f function times the partial with respect to the first variable, plus 1 over the g function times the partial with respect to the second variable, times v hat, plus 1 over the third function times the partial with respect to the third variable, times w hat. So in Cartesian coordinates, remember, f, g, and h were all 1, okay? So if we divide these by 1, and we replace u, v, and w by x, y, and z, we get the gradient is equal to dt dx x hat plus dt dy y hat plus dt dz z hat, okay? Which is what you are hopefully remember from a couple classes ago. In spherical coordinates, again, as you'd expect, not so simple. Well, not too complicated, but f was equal to 1, so we'd have dt dr r hat times 1 over 1 plus dt d theta theta hat times 1 over r, because g is, the function g is r for spherical coordinates, we just showed on the last slide. And then dt d phi hat times the function h, which was r sine theta. Okay, and remember, these 1, r, and r sine theta are all coming from this elementary length unit written out in terms of dr r hat, d theta theta hat, and d phi phi hat, but you have to multiply by. Okay, so that's where they come from. Okay, the volume element is nicely quite simple. You just take dv is equal to the f function times the g function times the h function times du dv dw. Okay, so for Cartesian, we'd have f, g, and h are all 1, so they're all 1, times dx, dy, dz, and we get that the volume element is just dx, dy, dz, which is what you'd expect, just a little rectangular prism, I guess you'd call it. For spherical, again, it's more interesting because the f, g, and h functions are not all 1. We have 1 times r sine theta, since that's f, g times h, times dr, d theta, d phi. Okay. And notice this does have units of volume because we have r times r sine theta times dr. These two are unitless, so this has units of length cubed. And this is the r squared sine theta dr d theta d phi, which you may remember from multivariable calculus. But in any case, now you know how to find that volume element, assuming you can find the infinitesimal length element for spherical coordinates. Okay, the divergence and the curl are quite a bit more complicated, and these, but they're derived in Appendix A. If you care to derive them, I'm not going to hold you responsible for memorizing them. In fact, I'll give you these formulas on tests. but there's a certain symmetry to them. The divergence of a vector field A in an arbitrary orthogonal coordinate system is 1 over FGH, which is like 1 over a volume, which makes sense because divergence is per unit volume, times DDU GH and the U component of A plus DDV FH times the V component of A, the vector A, times DDW FG times the W component of A. Okay? So you can see it's there. If you look at this for a minute, you'll see that there's a certain cyclic pattern here. And again, you don't have to memorize this formula. But let's apply it. For Cartesian, again, you might try to remember the expression for the divergence in Cartesian coordinates. If it's not, just take a pause and try to remember what that is right now. Okay, if you've done that, you can see that if we plug in 1 for f, g, and h, which are the expressions for Cartesian, and then 1 for g and h, 1 for f and h, 1 for f and g, we just get 1 over 1 times ddx of ax plus ddy ay plus ddz az. And that's the formula which you hopefully remembered, dax dx plus day dy plus daz dz. Okay, so we get back the formula we expect for Cartesian coordinates. For spherical coordinates, I've written here these to remind us. We have 1 r and r sine theta. We get quite a complicated formula, as you might expect. I won't go through all of it. You can pause and verify that we've substituted f, g, and h correctly in here. We can see here that out in front we get f, which is 1, times g, which is r, times h, which is r sine theta, so 1 over r squared sine theta. And then you can verify that the rest of them correspond to these, what you get when you substitute in the f and g's into this top expression here. Okay, so not such a simple expression for the divergence in spherical coordinates. This expression can be simplified a little bit because notice this derivative with respect to r, it's a partial, so it doesn't affect this sine theta here. So the sine theta can be brought out in front and it cancels with this sine theta. And a couple other cancellations can be shown to occur. For example, this r is not affected by the partial with respect to phi. So this r can cancel one of the r's in the denominator here. So this is often simplified and rewritten a little bit more simply. And this is the formula which you should find in the front of your textbook here. But it's not really much simpler than the formula we've derived here, and we're deriving it from systematically using a general formula with our knowledge of our f, g, and h functions for spherical coordinates. Okay, and then finally the curl. The curl I won't even bother to try to read to you. The curl is pretty complicated in Cartesian coordinates. You'd expect it to be very complicated in general coordinates, and it is. And again, I don't expect you to memorize this formula. I will give it to you on tests, and you would be expected to be able to use g and h from spherical or cylindrical coordinates to find the curl in those coordinate systems. And there is a pattern to this if you stare at it for a while, but I won't go into it. So Cartesian, though, let's verify the Cartesian system again. Everything is 1. F, G, and H are all 1. So GH, FH, FG are 1. Everything multiplying inside here is 1. And so we get lots of 1s, and we get dAz dy minus day dz, x hat plus dax dy z minus daz dx, y hat plus day dx minus dax dy z hat. And that is, you may hopefully recognize it, but if not, that is the formula you get when you put the unit vectors x, y, and z, three partials here, and ax, ay, az, which is how you know how to take the curl in Cartesian coordinates. But I bet you may not have had any idea how to take the curl or get an expression for the curl in spherical coordinates. And you can do it. It is, again, it's going to be quite complicated. It is quite complicated, which is why we deal with Cartesian coordinates when we can. So f again is 1, the g function is r, and the h function is r sine theta for spherical coordinates. And we get this here, which is not going to win any beauty contests, okay? But it is something we could compute, and certainly, if not by hand, then using Mathematica for a given given expression. Okay, so oh, and it can be simplified a little bit. Again, as I said, because for example, this dd theta does not affect the r, so the r can, one of these r's can cancel this r, and several other simplifications can take place. Okay, so basically then, just to conclude, I'd like you to be aware that yes, you can look up formulas on the internet for the divergence and the curl and the gradient in different coordinate systems, and we all do that. But there is a systematic way that there, of course, is a way that they have to be found some way, and this is actually the way they're found. It's described in Appendix A, and I'm just presenting the results to you here in this class, that we first write the length element in the given coordinate system with the first coordinate times the unit vector, the second coordinate times the unit vector, the third coordinate times the unit vector, and then whatever we need to multiply each of those by to get the total differential length. And then we identify these length elements, f, g, and h, for the particular coordinate system. And then we can use general formulas to find the volume element, which is just fg times h, the gradient we saw before, the divergence we've seen, and the curl in the given coordinate system. Okay, so we'll be getting more practice. You'll be getting practice on this, so you get a feel for it with a new coordinate system you haven't tried it with in class on cylindrical coordinates. All right, thanks. See you in class.